Hi everyone. This video is one I've been working towards for a while. I've made a bunch of videos preparing for this, and I'm going to be comparing the cardinality of the power set of the natural numbers to the cardinality of the real numbers. And one important fact from a previous video that I proved there is that the cardinality of the real numbers is equal to the cardinality of the open interval from 0 to 1. And I also proved in a previous video that cardinality equality is transitive, and so instead of directly approaching this comparison, I'll instead be comparing the cardinality of the power set of the naturals with the cardinality of this open interval from 0 to 1. And if this is equal, then, well, this is a question mark. If this is equal, then the power set of the naturals has the same cardinality as the reals as well, due to transitivity of equality. So now let's look into whether or not this is equal. As always, we want to try and look to see if there's a bijective function from the power set of the natural numbers to the open interval from 0 to 1, or prove that there is no bijective function that exists between the two. So I recommend you pause for a minute or for a few minutes and try to think about this. It can be tricky, so yeah, take your time. But yeah, I really encourage you to try it on your own before continuing. Anyway, I'll go ahead now and show you the solution. I hope you did figure it out yourself though. So yeah, I'll reveal the answer, which is that in fact, these two sets do have the same cardinality. And again, we'll be approaching this first from comparing it to that open interval from 0 to 1. And the way you want to do this is creating a one-to-one correspondence from elements of the power set of the naturals to elements in 0, 1. And recall that the elements of the power set of the naturals are subsets of the natural numbers. So the empty set is one subset of the naturals. The entire set of natural numbers is also a subset of the naturals. Then anything containing any number of natural numbers, any set containing any number of natural numbers is also a subset of the naturals. So these are all elements of the power set of the naturals. So how might we try to create a one-to-one correspondence with the elements of the open interval from 0 to 1? Again, this is just any real number between 0 and 1. That could be 1/3. It could be 0.7. It could be I don't know if it could be e minus 2, because e is I just wanted to include an irrational number. E is irrational, and it's something between 2 and 3, so e minus 2 is an irrational number between 0 and 1. Just wanted to make sure I included an irrational number here. So all of those things are elements of this open interval. So how might we create a one-to-one correspondence between these two sets? So here's one way, and this is going to rely on first converting real numbers into binary notation. And in the previous video I made, I showed how binary works, and also that you can write any real number in binary. So suppose you have some real number which is in this open interval from 0 to 1, then that means that you can write it as an infinite series of decimal digits. And yeah, that's all you need to know about it right now. And for now, that's all it means for it to be a real number, and this is assuming base 10. But then we can convert it to decimal, in which case it's just some series of ones and zeros. It can look like really anything, and it can be infinite, an infinite sequence of ones and zeros after decimal point. And you can represent any number in this open interval like this, and they'll all look different. So yeah, now might be another time to try this problem on your own, the rest of it, to see if you can solve it if you didn't already. But yeah, I'll now show you how to do that. Essentially, so first we can try and look at an example. So suppose that this doesn't go on forever, that it's not an infinite decimal, and instead that it's just it just stops here, and it can still be written as an infinite decimal with infinite zeros following this final one, but it can also be truncated and just look like this. So then we might try to think of what might be a unique way to a unique subset of the naturals that we can map to this in some sensible way. And I'll give that to you. I'll do it in a different color. What set? So we can do it like this. The first digit after the decimal has a 1, not a 0. So in some sense, that's, you can think of 1s as included and 0s as not included. So in this case, the first element is included. So 1 is included, so you can include 1 in this subset of the naturals. Then 0 is not included, so this is the second digit, so you don't include 2 in this subset. Then 3 and 4 are included, 5 is not, 6 is, 7 is not, 8 is not, 9 is not, 10 is, 11 is. And everything else after this is 0, assumed since we stop it here, and so that's it. That's the subset of the naturals, which is an element of the power set of the naturals, which can be mapped to this, and there's some kind of like sensible way in which we've connected these two things. And this actually works in general. You can write even an infinite binary decimal. Every time there's a 1, you can just add the decimal place, the place of that 1 to the associated subset of the naturals. And subsets of the naturals can themselves be infinite, so that also works. Again, like the naturals are themselves a subset of the naturals, so that's clearly an infinite set, which is a subset of the naturals, so that kind of shows that even with an infinite binary decimal, you can have an associated subset of the naturals. And this is basically all there is to say in this proof, that that you have the elements in this associated set are the set of all decimal places where there's a 1 in the associated real number between 0 and 1. And yeah, this is another one where the function is like difficult to write explicitly, but it is clear that it is a bijective function, which again, how do you know this is true? There's one and only one subset of the naturals associated with every binary real number in this interval. And it's clear that you can look at the binary and come up with a unique subset of the naturals. And similarly, you could look at a subset of naturals. Let's just come up with a new one for the sake of showing this. So what's the binary decimal associated with this subset of naturals? That would be, since the first decimal place should be a 1, the second isn't there, so no, 3 and 4 are, and that's it. So you can see that you can come up with a unique subset of the naturals for each binary, and a unique binary for each subset of the naturals. And therefore, this is a bijective function from the power set of the natural numbers to the set of all numbers in this open interval from 0 to 1 expressed in binary, which is really the same set as just 0 to 1 in general. And so the cardinality of the power set of the naturals is equal to the cardinality of the open interval from 0 to 1, which is equal to the cardinality of the real numbers. And yeah, that's the end of the proof, essentially. And just to add one more thing, we said before that the cardinality of the power set of any set A is equal to 2 to the power of the cardinality of A. And this justifies why we sometimes call the cardinality of the continuum, which is denoted as C. We sometimes also say that this is 2 to the power of aleph null, aleph null being the cardinality of the natural numbers, and the cardinality of the continuum is larger than the cardinality of the natural numbers than aleph null, but it can be written as 2 to the power of aleph null for this reason. And just a reminder of the interesting fact that the continuum hypothesis is that there's nothing between aleph null and 2 to the power of aleph null, or the cardinality of the continuum. And that's a hypothesis which is either provable or disprovable. Yeah, that's about all I have to say. I hope you enjoyed seeing the proof. comparing the power set of naturals to the cardinality of the reals. Thanks for watching.